All right, hi everybody. What is going on here? There we go. Okay. So today we are going to be circling back to this notion of solving systems. And we're going to tie this back into using matrices that we've been talking about here recently. So we're going to tie these two ideas up into a nice little bow. How's that sound? I know I'm excited too. Yes.
Are we allowed that?
Not at this time. So we're going to be looking at three methods. Okay, so those three methods are Gaussian elimination, Cramer's rule, and a matrix equation. I read those out of order for some reason. Probably I had a little tiny stroke at that exact moment. That's a joke, guys. I didn't have a stroke. All right. So let's just kind of do an example of these through how we could go about doing those in the midst of an example. Okay with that plan? So I'm going to start with a relatively straightforward example of just a two-variable system. And we'll talk about how you could scale into a system of really any size. So this first example is going to be solving this system using a matrix equation. So the first thing that I'm going to do is talk about how we can kind of do the setup. And I'll do the setup here naively, and then we'll talk about what you would need to do in order to just go directly from our system to our matrix equation without having to do some of this intermediate gobbledygook. But I feel like it's necessary to kind of justify why we get, rather than just like making it magic and going straight there. So what I want to start by doing is making this 2x1 matrix equal to this 2x1 matrix. And this is equivalent to the system I've written before, right? Yes, thank you. Because for this matrix equation to hold, the corresponding elements of each matrix have to be equal, which is the same thing as what we have in our system, right? Everybody's okay with that idea? So this 2x1 system that we have on the left could have been the product of a 2x2 matrix times a 2x1 matrix. And is I'm going to try to get the constants in one matrix and the variables in the other matrix. Everybody's okay with that? That's kind of what matrix multiplication would have looked like, right? This is weird because we're going backwards a little bit. But hopefully when I kind of do the highlighting, you can see how I went and did the backwardsness there. And if we do the same thing, then we have this. And this is what we're going to call our matrix equation. So if I look at this matrix on the far left, how could I have gone straight from the system to that matrix? So I'm looking at the system, and I'm looking at this first matrix. Do you notice anything about those two things? The coefficients are exactly the same locations as the elements in our matrix are. You guys kind of agree with that? Okay. For that reason, we refer to this first matrix as the coefficients matrix. Because it's made up of the coefficients of our problem, just in the same position and same order that they would appear in the original. This next matrix we call the variables matrix. It just has the variables from our problem kind of in the same order as they appear in our equations. And the last matrix we call the solutions matrix because it's just made up of the solutions for our system in the same order that they appear in our system. So it's pretty easy to go from the matrix or from the system to this matrix equation, right? Does everybody agree with that? So for the sake of argument, I'm going to refer to this first matrix as A, the variables matrix as X, and the solutions matrix as B. So what we really have is AX is equal to B. Okay. Is everybody okay with that? We're now going to do a little bit of algebra here to get to a point where we can solve this equation. So just as a analogy, let's say we have the regular old equation 2x is equal to 4. You see how this is similar in setup to ax equal b? Now, in ax equals b, ax and b are all matrices. 2x or 2x equals 4 are all numbers, but we can kind of follow a similar algebraic pattern. So if I was solving 2x is equal to 4, what would I do first? Divide by 2. Fair enough. Can I do the same thing with matrices? Can I just divide by A? No, why not? There's no such thing as matrix division. Okay, well, let's go back to 2x equals 4. If I told you I don't want you to divide, what would you do instead? Multiply by the multiplicative inverse of 2, 1/2, right? So what should we do to solve ax equals b? Multiply by determinant, the inverse,
yeah, that.
right? So we want to multiply both sides of this equation by A inverse. Now, does it matter the order that we multiply things with matrices? Yes. So we have to be very careful about how we're about to do this. So on the left side, AX side, where do I want to put the A inverse? Before the A, after the A, or after the X? Before the A. Good. Now, on the right-hand side, where do I want to put the A inverse? Before the B or after the B? That is incorrect. Has to be before. Why? Yes, the dimensions. A is a 2 by 2. B is a 2 by 1. I cannot have them in the opposite order. Everybody agree with that? Okay. So what happens if when I multiply A inverse times A? What do I get? I get what? 1. But in matrix land, what do we call 1? It's the identity matrix that we called I. Remember, that's the matrix with 1s down the main diagonals and 0s everywhere else. And what do we get when we multiply the identity matrix by X? What's the identity matrix act like? 1. So we just get X. We all okay to here? So now we're left with a problem that we can solve. Everybody's okay to this? So to do the inverse, we have 1 over 42 minus 12, which is negative 54. So 1 over negative 54. Then I switch the locations along the main diagonal, and I negate the elements on the other diagonal. Are we okay to here? Now I have 3 things to multiply. I'm going to choose to do these 2 first. Why would I choose to do that? It's a very practical reason. I want to avoid having to add and subtract fractions. I'd have to do that if I multiplied the fraction into one of these matrices before I did the multiplication. If I do the matrix multiplication, I'm just going to end up with a 2 by 1 matrix, and then all I have to do is multiply the other one in, so the worst I'd have to do is reduce, because multiplying a whole number to a fraction is pretty easy. Adding 2 fractions can be a pain in the ding-dong. Okay. So let's do that. So 6 times 18 is... oh, what is that? 108, I think. And then negative 2 times 0 is 0. Negative 6 times negative 18 is negative 108. And 7 times 0 is 0. And so 108 plus 0 is just 108. And negative 54 times 108 is negative 2. Negative 108 plus 0 is negative 108. And negative 1 over 54 times that is positive 2. So remember, X is the matrix XY. So this tells me X is negative 2, Y is positive 2. Or our solution is negative 2, 2. What are the potential drawbacks to this method?
Or is it like short in terms of
well, takes a long time. Well, I would argue that it's no longer than the by hand methods that we did. Because here's the issue, Sergio, is that like this is the same every single time, right?
Yeah.
So you don't really have to do that. That's always the same. So really the only solving step is this, which isn't so bad. Really no worse than substitution or elimination was. So, yeah, drawback, I don't know. I don't think it's that much worse than the things we've already been doing. You could argue with that, but there's some other things that I think are bigger issues away. One of which I think is pretty obvious, the other of which I think is maybe less obvious. So let's imagine this. What if we had a 3-variable system? What kind of problem would that cause for us right now? You'd have a 3x3 inverse, right, that you'd have to find. Do we know how to do that? No. So what are we going to do in that case? Or what could we do in that case? I'm not going to ask you to do that by hand, but what might I ask you to do it by?
Our calculator.
Using a calculator. Did you know your calculator can do all these matrix operations on it?
Yeah, I had to check my work in the lab.
Some of you may have figured that out by now, others of you may not have. Let's run through how to do that. In the interest of just time, I'm going to not give a 3x3 or 3-variable system example to show you how to do the calculator because it doesn't really change anything. I'm just going to do it with our current example here just because it's less stuff to type in. Is that okay with everybody? But nothing would change as far as the calculator part goes other than the size of the matrices you're entering into your calculator. Okay. So, where we're going to go is to the matrix menu. You can access the matrix menu by pressing the second button and then the x to the negative 1 button there on the left-hand side. Everybody found it? To type a matrix into our calculator, we need to go to the Edit tab. So use your left and right arrows to move to the Edit tab and pick one of these matrices to use. I'm going to pick this first one, matrix A. Mine has something in it already. That's what the 2x3 is indicating to us. Most of you guys, it's probably nothing there. So the first thing I'm going to do is indicate the dimension of the matrix that I'm going to type in. The matrix I'm going to type is the matrix A that we just were dealing with before, which is a 2x2. So I'm going to press 2, enter, 2, enter. And then I'm going to type in the entries to my matrix exactly as they appear on my sheet of paper. So -7, +2, +6, +6. Amy? So what? Second, and then the x to the negative 1 button. You should see the word matrix in blue above that button. You're welcome. And then you go over to the Edit tab and select a matrix to work on. Okay, so we're going to exit out to the main screen again. So second, and then the mode button right next to it. And we're going to repeat that same process, but this time we're going to use matrix B, and we're going to type in that matrix 18, 0. So I'll press second, x to the negative 1, move over to the Edit tab, go down to matrix B. This is a 2x1, and the entries were 18 and 0. Once I've done that, I'm going to exit back to the main screen again. At this point, you should have 2 matrices. Type it into your calculator, a matrix A and a matrix B. Is anybody still working on that part? Okay, very good. What I'm going to type into on my calculator now is simply the same thing that I have on my paper right here. I'm going to type in A to the negative 1 times B. So on my calculator, to retrieve matrix A, I'm going to go back into the matrix menu. And under the Names tab, I'm going to select matrix A. And then I'm going to press that x to the negative 1 button and press the multiplication key. And then I'm going to go back into my matrix menu. And this time from the Names tab, I'm going to select matrix B so that I have A inverse times B on my screen. Once I have that, I'm going to press enter. Boom. That's pretty righteous, right? So now, if this is a 3-variable system, this is going to be much faster, correct, than doing a 3-variable system by hand. What if it was a 4-variable system or a 5-variable system? This becomes massive improvement now, right? That's pretty righteous.
Show me how you found it.
Go back to the matrix menu. From the Names tab, just select the matrix B that you made a second ago. So just use your up and down arrows to move to B and press enter to select it. Now we've eliminated the drawback of having to find the big inverse, because the calculator is just can handle that for us, right? There's still another potential pitfall here that we have to worry about using this method. This one's a little more difficult to see. Anybody with a guess as to what the other potential pitfall is to this method? Well, if we have 3 variables, that's not a big deal. We just use a bigger matrix, and the calculator can handle it really quickly. Do we always have to get a single answer when solving a system? What else could happen? If I have to get Z in a 3-variable? What do you mean by we always have to find Z? I'm confused. I'm not sure I understand what you're asking or what you're saying. Are you sure?
Yeah.
I mean, okay. What else can happen on these kinds of problems? You can get no solution, and there's another thing that could happen. You could get infinitely many solutions. What's going to happen there? If I try to find what's going to happen there?
Let's say error.
What kind of error are we going to, why would we be getting an error? You're right, it is going to cause an error, but why? Well, as just a little example, what's the solution to this system? You should be able to do this easily in your head. That has no solution, right? Everybody agree with that? If you did elimination and you just did A minus B, you'd get 0 equals 1, right? Everybody agree? In this case, A would be the matrix 1, 1, 1, 1. The problem is A inverse is undefined. Similarly, what if we had the system what's the answer to this system? That's infinitely many solutions, right? You can tell because one equation is just a multiple of the other. Here, our A matrix would be 1, 1, 2, 2, but still A inverse is undefined. So we're not going to be able to tell the difference between a no solution situation, an infinitely many solution situation with this method. That's our major drawback to it. And now, in these examples I gave you, it was trivial to tell which one was which. Was that always the case? No. You remember the 3-variable solving sheet that I gave you, that they were all either infinitely many solutions or no solutions. Some of them, there was no easy way to tell just by looking at the problem what the deal was, even if you knew what to look for. And it gets more, that's more difficult to tell the bigger the system gets, right? 2 variables, it's easy. 3 variables, sometimes it's easy. 4 variables and up, it's like rarely going to be easy. So we should probably keep looking for another method, although this one is pretty righteous. Let's do Cramer's method now. So I'm going to use this same matrix that we just used. And Cramer's method is just a formula. It tells you how to find the system or find the solution very quickly. Actually, let's do this in general, and then we'll do it over here. So Cramer's method relates our solutions to our variables just to determinants of some matrices. Now the denominator of that relationship, that matrix is easy to see because it's just the coefficients matrix. Is everybody okay with that? The numerator for each of these fractions, the matrix is easy to tell or easy to see because it's just a modified version of the coefficients matrix. So if I'm solving for x, I'm just replacing the column where the x's are in my coefficients matrix with the solutions column. If I'm solving for y, I'm just going to replace the column where the y's are in my coefficients matrix with the solutions. If I had a 3-variable system, to find z, I would replace the z column with the solutions. Same, no matter how many variables you have, that's the basic setup. Is everybody okay with that? Okay. So let's do that here for this problem. So the denominator is just going to be the determinant of the coefficients matrix. And the numerator is going to be, I'm going to replace the column where the x's are in my coefficients matrix with the solutions. And then everything else stayed the same. Now, if I do the y's, the denominator is still the determinant of the coefficients matrix. The numerator is going to be the same coefficients matrix, except I'm going to replace the y column with the solutions. And then everything else stays the same. So these determinants are easy to calculate. 18 times 6 is 108, thank you. Minus 0 is just 108. Negative 42 minus 12 is negative 54. So that's negative 2, just like we saw before. Negative 7 times 0 is 0, minus 6 times 108 is negative 108. And then that's the same denominator. So I get positive 2. And I'm done. What's the drawback here? What if I have a 4-variable system? Do you know how to take the determinant of a 4x4 matrix? No? Do we have a tool that will do it for us? Yes. So let's do this same problem here with our calculator. Obviously, if it's a 3 or 4 variable system, you'll have different size matrices and more of them because you have to solve for x, y, z, etc. But this is enough of an example to get you a feel for how you do it, right? Is everybody okay with that plan?
Can you just explain how you got like 108 and then the answers without?
So this times that minus this times that. That's just the definition of how we take the determinant for a 2x2. And I did that for each of them. You're welcome. All right. So I'm going to go back into my matrix menu. Going to go over to the Edit tab. Our matrix A is going to be the same matrix A that we typed in earlier, so I'm not going to bother to change that. But matrices B and C I am going to change. So matrix B is going to be the numerator for the X variable. So that's 18, 0, and then 2, 6. And then I'll exit back out, go back in, go to the Edit tab, go pick matrix C, make another 2x2. This one will be negative 7, 18, 6, and 0. And once I've done that, I'm going to exit back out to the main screen and wait for everybody to get their stuff typed in. Amy. It's the denominator in these fractions here. So negative 7, 2, 6, 6. It was the same one as the same coefficients matrix that we used in the earlier version, so I didn't bother. It's the advantage of doing the same problem over and over again in the order that I'm choosing to do these methods. What? Yes, they're all 2x2s. Yes.
Can you explain I did that?
Did what?
Like the calculator.
I pressed second and the X and the negative 1 button to go into the matrix menu.
Yeah.
I used the left and right arrows to go to the Edit tab. I selected a matrix that I either wanted to change or edit. Made the dimension 2x2, and then typed in the entries as they appeared on my sheet of paper for whichever one we were typing in. We already have matrix A done. It's the same matrix A from the previous problem. Is that what you needed, Sergio?
Yeah.
Okay. Once you've done one, you have to exit out and then go back in and edit the next one, though. There's not a way to just step back one plate, like one menu in this on these calculators, which is kind of unfortunate. But Maya. I put in the numerator for x. So 18206 is what I put in B. And then in C, I put the numerator for the y here on the board. Is that okay? You can see what I'm pointing at? Maya? Okay. I can't see, all I can see like this much of your face. So like if you really have to respond yes or no, or else I just don't know if you're okay or not. And if you're not, you can say that and be like, no, I don't know what you're pointing at. You're good? All right. So now I'm going to set up these two fractions. So I'll do alpha y equals and pick the first option to make a fraction. In the numerator of the first fraction, I'm going to do the determinant of b. To get the determinant command, I'm going to go into my matrix menu. This time I'm going to go into the math tab. And the very first command is det, that's short for determinant. So now I have the determinant of something in the numerator. I'm going to go back into my matrix menu and retrieve my matrix B, which is where I typed in the numerator for x here. I'll close my parenthesis, move to the denominator, and repeat that same process. This time the determinant of A is what I'm going to put down there. So into the matrix menu, over to the math tab, select the determinant command, back into the matrix menu, select matrix A, close my parenthesis, and press enter. So that's our answer for x. To get our answer for y, the only thing we need to change here is the value for c in the numerator, right? It should be the determinant of c and not b. So the easiest way to do that is to just edit what I had previously. So if I use my up and down arrows, then I can go back and select this matrix and press enter. And then if I use my arrows, I can go back into where I have matrix B. And then if I go back into my matrix menu and select matrix C, it'll just put it on over top. And then I can press enter without having to jump through all those hoops, going through all the menus again. Or you could go through all the menus again. It's not a big deal. Alyssa.
Where do you find like the determinant on the
Matrix menu, over to the math tab, command 1. Tell me if you find it.
how do you do the matrix?
Second, x to the negative 1. You'll see above that button in blue is the word matrix.
Okay, thank you.
You're welcome. So that, again, the blue words above the buttons means you press the second and then that button to access that menu. Again, it's the first time you're using these calculators to do this stuff. It's okay to ask the same question over and over again. No big deal. I'm just trying to help you learn how the calculator is set up and remember where things are at. And again, I'm recording all of what we're doing, so you can always go back and watch the video while you're doing the homework to kind of walk through how to do these things on the calculator, again, if you forget. So that's always there for you. Okay. Draw back to this. So using the calculator, we don't have to worry about the big determinants. The calculator will take care of a big determinant for us. What's the drawback here? Well, it's the same issue as the matrix equation one, right? If we have no solution or infinitely many solutions, the coefficients matrix is going to have a determinant of 0. Remember, it had The inverses didn't exist because they had zero determinants. We're going to have a zero determinant there. If I have a zero in the denominator of a fraction, that's going to give me undefined. Zero in the numerator is zero. Zero in the denominator is undefined. So again, we're stuck there and can't tell the difference between no solution and infinitely many solutions. Okay? On to the last example, which is Gaussian elimination. And again, I'm going to do the same system that we've looked at a couple of times now. So our setup for Gaussian elimination is the easiest setup yet. We're going to create this matrix that looks exactly like my system. I've just dropped out the addition and subtraction equal signs in the variables. So I just took all the number parts that are in there. We call this an augmented matrix. I don't know why it didn't switch to red. Let me switch to red here. We call it an augmented matrix because it's the coefficients matrix with a little bit more. We have one extra column on there. Can we all see that? Okay. So what we're going to do now is we're going to do this process called Gaussian elimination. And the result that we're going to be left with is a matrix that looks like the identity matrix, and then with a column where our solutions are. This type of matrix is called row-reduced echelon form. I don't think there's an S in there. The beautiful piece of Gaussian elimination is that this is an algorithm. That it's the same steps every single time. And because it's the same steps every single time, this is programmable. So we can design a computer program to execute this Gaussian elimination every single time, no matter what the input is. That's lovely. So what does this Gaussian elimination look like? Just to give you an idea. So the first step is to switch rows in row 1 so that the first entry is non-zero. If the first entry is already non-zero, we don't have to do anything. Second step, multiply all the entries in row 1 by a number so that the first entry in row 1 is 1. Then we're going to multiply row 1 by a number such that when row 1 is added to the first entry is canceled. We store 2 rows in row 2. And then we repeat step 1 until all the other entries or repeat step 3, excuse me, until all the other entries in column 1 are 0. What is this starting to sound like? It should remind you of elimination, where the goal was to cancel out variables, right? So you guys kind of remember doing that, where you'd multiply the 2 equations by something, add them together so the variable canceled out. It's the same general principle. So this is just eliminating all the variables except in one equation from the first column. Then we're going to repeat the same thing for each of the next columns until you have in the second column or in the second row, you're eliminating everything except for column 2. And then the third row, everything except for column 3, etc. Am I ever going to ask you to do this by hand? Nope. Why? Because your calculator has it programmed into it, and it can do it for you. So let's see how to do this. I'm going to go into my matrix menu. Go to the Edit tab. Using matrix D, I'm going to type in the 2 by 3 matrix that we just wrote down just a moment ago that you can no longer see on the page. Let me scroll up to it. There it is. -7, 2, 18. I'm going to stop reading numbers because it probably makes it harder to type numbers into your calculator when I'm saying them at the same time. Once I have that augmented matrix typed in my calculator, I'm going to exit out to the main screen. Anybody still typing? Okay. Now that we have that typed in, we're going to go back to the matrix menu, over to the Math tab, and we're going to scroll down. We are looking for the command RREF. There it is, Command B. Make sure you pick RREF and not REF. There is a difference. You want RREF. I'm going to select that command. And what am I going to do RREF on? That augmented matrix, matrix D that I just typed in a moment ago. And I'll press enter.
You get that RREF.
Matrix menu, Math tab, Command B, near the bottom. By the way, RREF stands for row reduced echelon form, in case you didn't put that together. I didn't mention it. You probably figured that out by now. You're bright, but help you remember which one you want. Okay, so somehow this contains our answer, right? Well, let's explain to you how to read the answer out of here. Each row corresponds to an equation. So the first equation would be 1x plus 0y equals -2, which just means x equal to -2. The second row corresponds to an equation. It says, or just y is equal to 2. Boom, you're done. Any problem scaling this to 3 variables? Nah. I mean, it's a different size matrix, but your calculator is just going to take care of it for you. And here's the best part. No problem with a no solution or infinitely many solution situation. Let me show you how to tell the difference using Gaussian elimination. So let's just say we have this super trivial system here. If we type this into our calculator and do the Gaussian elimination, let's just do it, right? It's no problem. So into the matrix, edit tab, matrix E, enter, 1, 1, 2, 1, 1, 1. And then command RREF on my matrix E. Which one of these 2 rows is the one that tells me that there's no solution? The second row. What does the second row say? 0x plus 0y is equal to 1, or 0 equals 1. Wah, wah, wah. Everybody okay with that? Let's look at how we can tell a infinitely many solution situation. And even better, I can easily use the result of Gaussian elimination to give the parametric solution to this system. So let's say we have this system. So this will be a 3 by 4. 2, 1, -3, 0. 4, 2, -6, 0, 1, -1, +1, 0. Exit back out. RREF of my matrix F Now I got some goofy looking decimals here. I prefer to have fractions, right? If I press the math button and use the fraction command, it'll go and take that matrix and rewrite it with all fractions in it. That's pretty rad. Thank you, Mr. Calculator. So I got this result. Which one of these rows tells me that this is infinitely many solutions? The last one, right? What does that last row say? 0x plus 0y, just 0 equals 0, just like it happened before, right? Totally radical. Now to get my parametric solution, the first row, and I can rewrite this just as x equals 2/3 z by adding 2/3 z to both sides, right? Everybody agree with that? So that tells me my first component to my parametric solution is 2/3 z. That's what the x's are. And the last component is going to be like my independent variable. That's just the z because I've written x in terms of z's. I can then take the second row and rearrange that to just be y equals 5/3 z. So that tells me the second component, my y's, and boom, parametric solution, done. That's pretty rad, right? That this matrix that tells me not only infinitely many solutions, but gives me the equations that I need to generate my parametric form all in one step. It's exciting, guys. It is exciting. Taylor, what are you squinting at? Is that the part you needed? Okay. You can ask if, like, can I zoom into a part, and I'm happy to try to help you out there. Or if the color I'm using is bad, you can tell me, like, hey, can you use a different color or whatever. Oh, no. No, tell me your name. Aaron. So you press the math button, and then the first command is frac. You select that command and press enter again, and it'll give you the same answer as a fraction. Did that work? Come show me what your calculator is. Okay, so we're not in the matrix menu. We're pressing the math button, not the math menu.
Okay.
And there's fraction.
Okay.
Boom.
Thank you.
You're welcome. Yes, sir.
Why is it 2/3 z, x is y, and z?
Oh, shoot. That was supposed to be a z. Yes. Go ahead, Maria. Supposed to be a z. Thank you very much. Because it's just this part. Good call, Luke. Sergio.
Say, like, use the specific method or we use it.
Ah, so good question. So, like, come test time, what is my expectation going to be? There's going to be a portion of the test where I'm going to ask you to solve things with either substitution or elimination, but I'll tell you to check your work using Gaussian elimination. Okay? So, again, now you have the right answers for the substitution elimination. You'll know during the course of that whether you've made a mistake or not right away before you go and do the whole thing. Like as soon as you get your first solution, you'll be like, oops, something went wrong there, right? Which is wonderful. There'll be another part of the test where I ask you to like solve using Cramer's rule, but I want you to do is show me the setup and then use your calculator to do the matrix calculation. Or solve using a matrix equation, just show me the setup, like show me the matrices and what you typed in your calculator, and then use the calculator to do the matrix calculation. Because in all reality, like some of these things are rather time consuming, and in a time setting, you don't have enough time to like do everything that by hand, right?
Or if you're like adding matrix, like we just add that.
So the matrix, I will have a matrix operation section. I would expect those to be done showing enough work that you can justify that you did it by hand, although there's no reason why you wouldn't check your answer at the calculator, right? Whether it's matrix multiplication or, a determinant or whatever, like I expect to see the work, but I would check my answer on the calculator, right? You know what I mean? So for you guys can now do homework here. So if you downloaded everything from the content library right away, I think a couple days later I came back and like did an updated version of this because I didn't like the format I had before because it was just turning into too many things. So the directions are here: Cramer's rule and Gaussian elimination. But in each one of these, I ask you to use your calculator to do the matrix operation. I don't need you to spend a million years like doing these determinants by hand or these inverses by hand, or I didn't even tell you how to do Gaussian elimination by hand. I just kind of like hand waved at like what the calculator's doing and then said use the calculator to do it. So that's what you guys will do for your homework tonight. The plan for Wednesday is we'll kind of work on the test review and kind of take general end of chapter questions. And then test on Friday, maybe. We'll kind of see how things are looking on Wednesday. Is that okay? As an agenda for the week. Hi, Maya. Yeah.
That's what we did for the term.
Okay. So we're going to do the formula. So I'm going to make a fraction. Do you know how to do that? I press alpha and then y equals. This is a shortcut to the fractions menu. And then this first option is the one we want. We're just like a numerator with it on. Okay? Now I'm going to go and I'm wanting to do the determinant of b over the determinant of a. Okay? So I'm going to go into the matrix menu. I'm going to go to the math tab. I'm going to select the determinant operation. And I'm going to do that on the matrix B. And then I'll do the same thing. Now I want the determinant of A. So go back to the matrix menu. Over to the math tab. Select the determinant. Go back to the matrix menu. Select matrix A. And then press enter. Cool? You're welcome. Sergio!
Why can't we just do like normal substitution or elimination?
You can. But that's not the point of the assignment. The point of the assignment is to practice these skills. But,
no, I know, but like, what's the point of these skills if we can just do it?
Well, imagine I give you a 5-variable system.
Yeah.
You know how many eliminations you have to do to solve a 5-variable system?
A lot of elimination.
Yeah, 2 to the 4th. So 32 eliminations.
Yeah.
That's one. Or 2 to the 4th, I don't know. But something, nope, it's way more than that.
Yeah.
But it's just an enormous amount, right? The bigger these systems get, the better it is to have a computerized method, which is the beauty of these. That are all things you can do on your calculator, and are reasonably fast to do on your calculator, too. So those of you that have an ACT or something to take here coming up this year, almost always you end up solving systems on the ACT. I would use the row-reduced echelon form to do all of those system solvings come standardized test time, because it's super fast, and I know I'm not going to goof it up. The last one, the Gaussian elimination.
The Gaussian elimination be the most useful Well, because I can tell which, if it's infinite or many.
Yes. And I think it's the fastest as far as your calculator goes because it only requires one matrix. You only need to type in one matrix and one command and it's boom, everything you need. So I think it's the easiest one to use on your calculator. It's the fastest one and it gives you the most information. You know, that's what I think anyways. And you can do a lot more with Gaussian elimination than just this, but you wouldn't know that until you take like a linear algebra course or something. But it's a good method.